So we're going to very soon be developing set theory, and I know you all are quite familiar with set theory and a lot of the concepts of set theory. You've probably studied them since high school or maybe even elementary school. Notions like subset, power set, domain, codomain, range, etc. are probably pretty familiar to you. What will be different in this class, though, is that we'll be developing set theory as an extension of predicate logic, which is what it really is. And quite possibly, since many of you hadn't really spent a lot of time with predicate logic, you wouldn't have been in a position to appreciate that set theory is an extension of predicate logic. What set theory is, essentially, is just defining a unique relation, and it's the one that you're familiar with, membership, which we represent with the Greek letter epsilon, and just really spelling out all the consequences of that. Now, it's within set theory that you also get a rigorous treatment of the notion of a function, which again is something that you're very familiar with from lots of different contexts. We're going to talk a little bit about functions right now before we develop set theory explicitly, because you can introduce function symbols directly into predicate logic and work with them even without really knowing all that much about what they mean or how they function in set theory. So we're going to achieve that level of understanding first, and then when we move on to set theory, we'll try to achieve a deeper level of understanding. So this lecture is just about functions introduced directly into predicate theory, into predicate logic without developing any of the other set theoretical concepts. So you might remember that we described propositional logic as truth functional, and that was not a casual use of the term. It's perfectly in accord with what we'll be learning here today. What it means to say that propositional logical operators are functions is that they take truth values as inputs and produce truth values as outputs. So this notion of function is identical to that of a mathematical function. You may have become familiar with the idea of a mathematical function when you took algebra and trigonometry and later calculus, differential equations, or however far you've gone in mathematics. Certainly familiar in computer science as well. For example, f of x equals x squared plus 3 is a function. If we plug in 2 as an input, we'll get 7 as an output. Input and output aren't really strictly the technical terms we use with functions. An input is what is technically called an argument, believe it or not, and an output is technically what we call a value. But in this informal introduction to functions, we are just going to stick mostly with the input-output terminology. So, in fact, you've been working with mathematical functions since long before high school and junior high school. You've been working with them since kindergarten. This is because some of the familiar arithmetical operators, like addition, plus, and subtraction, minus, are also functions. The only difference between a mathematical function and a truth function is that one operates on numbers and the other operates on truth values. So in predicate logic, we introduce a more generalized notion of a function, one that can apply to numbers, truth values, and just about any other sort of entity as well. In logic, the first important thing to understand about a function symbol is that it is really just a generalized naming device. The function f of x equals x squared plus 3, when applied to 3, which is really a name in mathematics, is identical to 12. 3 and 12 are both numerals which name numbers. In the language of predicate logic, we can represent some familiar relationships as functions. For example, we can let f stand for the biological father of. Suppose now that Alan is the biological father of Mei Lin. Then f of m is just another way of naming or referring to Alan. And unsurprisingly, we use the identity sign to express this. The father of Mei Lin is identical to Alan. So if the father of Mei Lin is identical to Alan, and Alan is a name, then the father of Mei Lin has to be functioning as a kind of name as well. So to repeat, the first thing to understand is that functions function as naming devices and specifically not as quantifiers or as predicates. This could be a little confusing because in predicate logic, we can also represent something like father of as a relation. For example, Alan is father of Mei Lin, can be represented as capital F A M. So functions and relations can indeed be used to convey similar information, but they're not the same thing. So let's try to be really clear about this. It'll help us to understand, among other things, the amazing power of the little word, the. So notice that there's a big difference between saying a man in the yard and the man in the yard. If I said a man in the yard peed on the lawn, then I'm not implying that there's only one man in the yard. There could be many men in the yard, and I'm just talking about the one that peed on the lawn. But if I say the man in the yard peed on the lawn, it usually means, strictly interpreted, that there is one and only one man in the yard, and he peed on the lawn. So the first expression allows of any number of men who may satisfy that description, but the second expression implies that there is one and only one man in the yard. So let's try to be really clear about this. Among other things, it will help us to understand the amazing power of the little word the. Notice that there is a big difference between saying a man in the yard and the man in the yard. The first expression allows of any number of men who may satisfy that description. I could say that there's a man in the yard, and that might sound like there's only one, but it's certainly logically possible that there's more than one. The second expression, the man in the yard, for example, the man in the yard just peed on the lawn, makes it very clear that there is one and only one man in the yard. This is called a definite description. The man in the yard is meant to pick out something specifically, just the way a name does. So the first expression allows of any number of men who may satisfy that description, but the second expression implies that there is one and only one man in the yard. That is one of the main differences between a function and a relation. If f is a binary relation, meaning father of, then capital F A B does not mean A is the father of B, even though we might sometimes just say that. In other words, it does not carry the information that B has one and only one father. Of course, nothing necessarily prevents you from defining the relation F to mean the one and only father of, but if you were to do this, you would be usurping the function of the existential operator. As you know, properties and relations that guarantee a thing's existence have a troubled history in philosophy. You may remember we've spoken of the ontological argument as having precisely that problem. So if I were to define F to mean the one and only father of, I would essentially be defining a relation as guaranteeing the existence of something. The other shortcoming of this approach is that even an expression like the one and only one father of doesn't capture the essential uniqueness of a person's biological father. You could speak of your one and only one bowling ball, for example, but this would not imply that a bowling ball is the type of thing of which we can have only one. For all we know, you may be the only person in the world who has only one bowling ball. This is why we have to be very careful about the sorts of things we characterize as functions. Usually, when we speak of a natural or social concept as a function, we're speaking loosely. Even biological father is problematic insofar as it is not impossible for a human being to be made mostly from the DNA of two or more human males, and if that were the case, we'd be very inclined to say that that person has two fathers. The least problematic examples come from math and logic, and even then, considerable work can be involved in proving that these are really functions. The other way to think about the difference between relations and functions is by reference to the is of predication and the is of identity. We introduced this distinction when we introduced the identity sign into the semantics of predicate logic. When we say Alan is a father of Bernice, we're predicating the relational property of fatherhood between two entities, A, F, A, B. But when we say Alan is the father of Bernice, we're saying that Alan is identical to the father of Bernice. And this carries the implication that a father is just the sort of thing of which one has one and only one. So to be a function, three conditions must be met. If, speaking informally now, in a function like f of x equals y, where x is the so-called input drawn from a set called the domain, and y is the output drawn from a set we call the range, the conditions are 1, every single input has an output, 2, identical inputs produce identical outputs, and 3, every input produces a unique output. Now these conditions can be summarized as for every input there is one and only one output. So function symbols work straightforwardly with quantifiers. For example, if we want to use a function symbol to say that someone's father is a crook, we would simply write there exists an x and there exists a y such that x equals f of y and x is a crook. Or even more compactly, there exists an x such that c f of x. There exists an x such that the father of x is a crook. So if we happen to know that the crook is the father of Andy, of course, then we would write, take off the existential quantifier and write crook father of Andy. Okay, so that of course would be just substituting A for X and getting rid of the existential quantifier. On the other hand, if we knew that the father himself was Andy, then we would say C A, right? And here A is being substituted, for f of x with the existential quantifier being removed. Okay, so there's two different kinds of substitutions you could perform here. One would be a name for x, the other would be a name for f of x. So functions can also be applied to other functions. In English, for example, a paternal grandfather is the father of the father. So we can say that Jared is Malin's paternal grandfather like this. The father of Malin equals Jared, is identical to Jared. Right? So this says the father of this individual, right? And this individual is the father of Malin. So the father of Malin. So this recursive property of functions, by the way, which allows us to make the output of a function into another input for that very function, turns out to be extremely powerful. So the possible inputs of a function can be thought of as a list of members in what we usually call the domain of that function. A function like father of takes a list with only one member and assigns one member from the range of that function, or a smaller subset, sometimes called the codomain. But other functions, known as n-place functions, take lists of two or more members of the domain. With regard to truth functional operators, negation is a one-place function. If we wanted to represent the way it works using functional symbolism, it would be something like this. Negation of t equals f. In other words, negation is a function that takes a single truth value, in this case true, as an input, and maps it onto the opposite truth value, which in this case is false. Conjunction, on the other hand, is a two-place function. It takes two truth values as input and gives one as an output. For example, conjunction, the conjunction function of tf is f. It's hard to come up with natural examples of multi-place functions, but we can do it by imagining weird worlds. Suppose, for example, that in a certain universe, every two people have exactly one mutual friend. Then letting f be the function mutual friend of, we can represent the statement, no two people have Melvin as a mutual friend as, for all x and for all y, it's not the case that x and y are mutual friends of Melvin. Or more precisely, for all x and for all y, it's not the case that the mutual friend of x and y is Melvin. Perhaps surprisingly, adding functions symbols to the language of predicate logic is very simple and requires only slight modifications to our understanding of the inference rules. Since function symbols are names that have parts, we need to distinguish between simple names and functions which are complex names. So this allows us to limit the restricted rules for the quantifiers, namely universal introduction and existential elimination, to simple names. And what I mean by this is, for example, if you're dealing with existential elimination and you have a formula, there exists an x such that f of x, and you want to do a hypothesis, you can go to f of a or f of b, as you know, as long as a or b are not already in a live hypothesis or assumption. But what you cannot do is go to, say, for example, f of, say, g, where g is a function of a, right? Technically, g of a is just a name, so you might say, why not? But the reason is because this name has some information in it. If, for example, G means maternal grandmother, you now know that A has maternal grandmother, and so that's not an arbitrary selection. So this restriction is necessary because it's impossible to select a name like G of A, F of A, since in doing so we're importing the fact that A, for example, has a father. It's interesting to see that the three basic properties of functions that we mentioned above correspond to theorems in predicate logic. The first property is that every input within the domain of a function has an output in the range of the function. If we drop reference to the domain and the range, this can be stated for a particular function f as follows. It's a theorem that for all x there exists a y such that y is identical to f of x. This theorem is easy to prove as long as you realize that just as a equals a can be introduced anytime in a proof by identity introduction, so can f of a equals f of a. So the rules for identity apply to functions just as much as to simple names. So you should stop the video here and do this proof. It takes exactly 3 steps. And I'm just going to show you the proof and then not talk about it, but move on because it's very simple. So the second property is that identical inputs produce identical outputs. And this can be roughly stated as for all x and for all y. If x is identical to y, then f of x is identical to f of y. And this is a very simple proof too. It's unchallenging in just about every way. But please stop the video and do it, and then take a gander at how it's done to make sure you're in good shape. The third property is that every input has a unique output. Since we have already proved that every input has an output, we can represent this as for all x and for all y and for all z, if y equals f of x and z equals f of x, then y has to equal z. So that's basically just telling us if you think of f of x, which is the output of the function, and you say that it's equal to y, and you say that it's equal to z, well, the only way that can be true is that if y equals z, because there is only one of them. So try this too. And again, it's a straightforward proof. You should stop the video and then check to make sure you've done it right. So when you become comfortable with functions, then it will be obvious to you how to do a proof like this. For all x, f of x yields f of g of m of AA. Now that looks like a mess, but it's a 2-step proof. If it isn't obvious to you why that's the case, stare at it for a while and try to remember what we said that functions are. They're names. The proof is 2 lines long, including the assumption. Prove that to yourself before moving along to look at the proof. So let's finish up by translating an argument, then trying to prove it. Harold's father loves Jenny's mother. If the father of anyone loves the mother of anyone, then either he is married to her or he's a cheat. If Harold's father is married to Jenny's mother, then Harold's father is Jenny's father too. So either Harold's father is Jenny's father or Harold's father is a cheat. Try the translation and then see if you can prove it. I'll go ahead and work through these translations and then give you the proof at the end. Go ahead and try it for yourself. Stop the video and try it for yourself. So Harold's father loves Jenny's mother. Loves Harold's father, Jenny's mother. So father of Harold loves the mother of Jenny. If the father of someone loves the mother of someone, then either he is married to her or he is a cheat. Now, I'm not dealing with the masculine pronoun here. For all X and for all Y, if the father of X loves the mother of Y, then the father of X is married to the mother of Y, or the father of X is a cheat. So notice, of course, that father of X, mother of Y, these are being treated as relations, but being married to and being a cheat are being treated as just relations and or property. You might briefly consider why we couldn't treat married as a function, but that's because not everyone is married, and a function is something that would have to guarantee that. If Harold's father is married to Jenny's mother, then Harold's father is Jenny's father too. So if the father of Harold is married to the mother of Jenny, then the father of Harold is identical to the father of Jenny. So either Harold's father is Jenny's father or Harold's father is a cheat. So it's a disjunction. So either Harold's father is identical to Jenny's father, or Harold's father of Harold, Harold's father, is a cheat. Okay, that gives us the full translation. All right, so if that's not quite the translation you got, go ahead and change it to that translation. Otherwise, you probably didn't come up with a valid proof, and then go ahead and try to prove it. I'll go ahead and show you the proof, and I won't talk through it, although I'll point out one small thing about it, which is that on line 7, it's immensely aided by the introduction of this disjunction, which is a theorem. It just has the form P or not P. In this case, MFHMJ, MFHMJ, or not MFHMJ. Otherwise, the proof is pretty simple. It takes advantage of the rule of constructive dilemma, which is just a version of a generalized version of disjunction elimination. And that's it.